Yeah, today we'll talk about deep neural network and how to quantify uncertainty and how to have a clue about how to explain the decision of the networks with a focus on medical images. So why do we need to explain the decision of the network? What do we need to quantify uncertainties? So now you know that you have a neural network to predict something from an MRI, for example, for an image. It can be a probability if you want to do classification. It can be a segmentation map if you, a map of probability if you want to do segmentation. And you don't know exactly how it is done. You know that there is a lot of operation with a lot of computation within the networks, but you don't know exactly how it is done, or at least you don't have a human understanding of what the operation means in terms of high-level knowledge. But you probably don't care always because it works well. You have a high performance, at least very high performance compared to what we had a few years ago on the same problems. In medical images or in critical domain, this can be an issue because you have a critical task to do. It can involve, for example, for medical in medical context, human life or human health or stuff like that. So you want a safeguard. You want to, for example, quantify the uncertainty. You have an answer from the network, but do you have an error associated with this answer? Are you certain of the class it predicts? And the second part of the talk is about can we have a bit of clue about the explanation why the network predicts what it predicts. So yeah, we'll go with that. So the source of uncertainty you can have in deep learning. Usually we classify them in two groups: the aleatoric uncertainties and the epistemic uncertainties. Aleatoric uncertainties is everything that related to the problem, to the task that is intrinsic to the task you want to solve. So for example, it can be the input noise, so the accuracy you have in the images that you use for the training or for the training. It can be the pre-processing. If you do registration first, you segment, you remove artifact. So this can be done with a certain precision. So this is a second source of error. You can have error in the ground truth that you use for the training. So it can be if you measure measure uncertainties. If you measure your output, it can be annotation noise, so intra or inter-operator variabilities, and also it's also the difficulty itself intrinsic to the task. So does your class overlap or not? Do you have a clear solution that can be found between the two classes if you have the classification, or does the class overlap? So all these difficulties, error, uncertainties are classified as aleatoric uncertainties. And then you have the epistemic uncertainties. So this is everything that is related to the training, or if you put it roughly. So it can be, you can also define it as everything that you can improve if you improve your training strategy. So if you have better results because you add more data, this is related to the epistemic uncertainty. So your model, your training, you do not have enough data. It can be related to the domain shift. Is the data on which you train are similar to the data that you will use in real life when you deploy your model in production? And it's everything that is related to the model, so the architecture, the training strategy, the optimizers, the learning rate, and so on, the early stopping strategy that you use. So for example, here, if you have these two classes and you want you would have the green bubble to represent the aleatoric uncertainties, so the overlap between the two classes, and the region of epistemic uncertainty is because you train your model on data that are shifted compared to the data you use for the test. If you go a bit further to detail the domain shift, the different domain shift that you can have a covariate shift. So the domain shift in the input distribution, input of the model. So for example, if you train all your data, all your model with data from a Siemens scanner, and then you use it on a GE scanner, well, you will have a domain shift because the images are not acquired the same way. You can have a label shift. So the label shift is related to the output. So if you change the repartition of the label, so if for example you train on a equilibrated data set, but in real life you have a very small pathological patient compared to the healthy subject, this will create a label shift, domain shift. And the concept shift is related to the relation between the input label, between the input and the label. Okay. What we talk about in this talk also is the confounders. So it's related to the bias in the data set, the bias that in this case is really obvious. You want to train a classifier to classify object based, and you want to classify them based on their shape. So you collect a data set and you put all the rectangular shape in one class and all the circles and ellipsoid shape in another class, and you train your model. But obviously here the classifier can base its decision either on the shape or the color, and you won't know what it will base his decision on. So here it's very easy to see that looking at this toy problem. In real life, it's more complicated because the confounder, the color in the previous slide, can be more subtle. For example, it can be the imaging parameters. So for example, if there is much more image from a GE scanner in one class compared to another, it can be the protocol that is used. It can also be related to the population. If you have only young people in one class and only aged people, can be related to I don't know, ethnicity. It can be is people living in countryside or within cities. So it can be more subtle and not easily seen just by looking at the data or the images. So the first part of the talk will be dedicated to uncertainty estimation, and then the second part will be presented by Valentine on the interpretability. So for the different tasks we can address, we can so the goal here is not having the output of the network as a class or as a segmentation map, but having an error estimation associated with the output. So for classification, you want to have the output, but more better, not only the class, but the probability to belong to a class, for example. Or it can be the set of class that can be potential candidate to the answer. If you do regression, you don't want an answer as a number, as a scalar number. You want an interval, a confidence interval, where the output belongs. If you have detection, can be seen as a per region classification. So you might want to have a probability associated with the location of each potential candidate object. And if you have segmentation, you want a segmentation probability map, or a map of only the error in certain location. So there is a lot of works dedicated to this task in the literatures. So here you have a review article that you can refer to if you want to delve more into this subject. And I'll present you only part of them, basically the ones that are in red here. And as you can see, regarding the aleatoric or epistemic detection, so aleatoric is in blue and epistemic is in green. So most of the work in the literature doesn't actually say whether they address epistemic or aleatoric. Some, about 30%, say that they are working on aleatoric uncertainties, only 5% on epistemic, and the huge majority doesn't say and doesn't address which kind of uncertainty they are revealing with their method. So the first very basic error measure you can think of, it can be for segmentation, it can be also for classification, is just basically the output of the network. For example, if you have the output of the network, at the end you have the softmax, and the output is a probability vector, something that is, you have a vector with components which are between 0 and 1, and that sum to 1. So you can say this is a probability vector, and this is a probability of being correct of your network. Unfortunately, you cannot interpret it that way. Why? Because networks, at least in modern neural network, are not calibrated. And what does it mean? So what are the calibration of a neural network? To understand calibration, we need to use a tool that is called a reliability diagram. So you have a network that is trained to predict a probability from an input x. So at the end, you have the softmax and you have these probability vectors. So, and you want to see if this probability vector is really the probability of x to belong to the class y that is predicted. So if you want to see that if you can interpret it, this probability, this output that way, what you can do is compute this diagram. So you have a data set with annotation, and you compute the output of this network, and that way you can compute the accuracy. Okay, but now what we are going to do is to not compute the global accuracy, but accuracy per output. By this, I mean, for example, you split 0, 1 into 3 bins, and you group the samples that predict something in 0 and 1/3 in one bins, in 1/3, 2/3 in the second bin, and 2/3, 1 in the last bin. Okay, you group the output, the samples per if they are confident or not in their prediction. So you have 3 bins, and then you can compute the accuracy within each of these bins. Okay. Okay, this is what you do here, and you can plot these values in this plot. So you have a plot with, in abscissa, the confidence, the output of the neural network, and in ordinate, the accuracy. So you have something like that. And if the network is calibrated, then if the confidence of the network is low, you want to have a low accuracy. If you have the high confidence in the prediction of the network, you want to have a high accuracy. So it's calibrated when these data are on the y equal x line. Okay, so this is a calibrated network. And if you so there is different case. If well, it's the opposite way, but if yes, no, it's not the opposite way. It's okay. So if you are on the left, you are underconfident. No, no, it's the opposite way. Underconfident. Yes. So on the left, you are overconfident. Okay. Because yes, all your prediction are higher than your actual accuracy. So you are more confident than you are accurate. You are well calibrated if your data are on the y=x line, and you are underconfident if you are not as confident as you are accurate. Okay, and from this you can also have a metric that is currently used, the ECE, which is the difference between your point and the y=x line, and the y=x line. Yes. And actually, modern neural network are often overconfident. The prediction is much more confident than they are accurate, because there is this paper which was written in 2017. So they investigate why, and they see that they're using a deeper neural network with large number of features, or layers such as the batch norm, make the neural network modern compared to the neural network of the 90s, really much more accurate, but much overconfident. And the cross-entropy loss, the use of the cross-entropy loss, is also one factor that make them more confident, because you push the probability to be very, very close to 1. Okay, and we will have some other thing about this later. So few methods to how to improve the calibration. So the first and very easy to implement things you can use is label smoothing. So for example, if you have a classification problem, usually, yeah, you train your network with the cross entropy, which yeah, the formula is written here, and the y here is a ground truth, so it's a vector with 0 and 1. Now, if you consider that you have that the ground truth is not ground truth, but you can be incorrect about the ground truth with a probability, well, incorrect with a probability epsilon, okay, or correct with a probability 1 minus epsilon. Then you do the derivation of the mathematical stuff, and what you end up with is you just have to train exactly the network, your network, the same way, exactly the same way, but you just replace your 0 or 1 vector by a vector with small values when it's does not belong to the class, or 1 minus a small values. Okay, so for example, instead of vector of 0 and 1, you have vector of 0.1 and 0.9. And doing that, you improve your calibration, because you do not push the probability close to 1, especially if you might have some incorrect labels. Okay, so this is very easy to implement. You just replace the 0 and 1 in the cross entropy by a small value or value close to 1. Another way to improve the calibration, so this way is a post hoc operation. So you train your network as usually, and then you replace the last softmax by exactly the same formula of the softmax, but you introduce temperature parameters. So you put yes, this T in the softmax equation, and then on the validation set, you adjust the T to make your network more calibrated. So this does improve very easily your calibration. And one last method that you can use to improve the calibration is, I told you the cross entropy was one of the reasons the network was overconfident. So you replace the cross entropy with a different loss. So instead of the cross entropy, you use the focal loss. Focal loss is just the cross entropy here, the minus log of the probability of the correct class, that you multiply by this 1 minus p at the exponent gamma. So here you can see the cross entropy in blue, and you see when p, the probability is close to 0, it goes to infinity, and when it's close to 1, it goes to 0, but with a non-negative derivative. Okay, so as long as you are not equal to 1, it will push the probability of this sample close to 1. And this is what you don't want to have. And just by multiplying by this 1 minus p exponent something, the curve, the loss look like that. So it's still, when the probability is close to 0, it still goes to the infinity. It will still go to 0 in 1, but now the derivative is 0, so it will be much harder to push the probability up to 1. So what's going to happen when the samples during the training are easy to classify? You will get a probability that will soon be close to something like 0.8. But then for these samples, it will be very difficult to go to 1, while for the label that the samples, sorry, that are more difficult to train, to classify, well, the network or the training will push the network to train weight to classify these samples. Instead of pushing the easy sample very close to 1, they will try to push the difficult one to a reasonable output. So all these methods help for the calibration. It will not solve the problem, but yeah, and they are all three very easy to implement. So this was about the calibration. So now it was, yes, does my network output something that I can interpret as an uncertainty? And now there is different way to measure or quantify uncertainty. So we start this part with Bayesian neural network. So what is Bayesian neural network? So neural network, you have the input, you have some computation, some units. Yeah, you can see all the units where you do basically dot products with between the input and the dot product with some weight. It gives you the output of the unit, and then you recombine all the output until the end of the network. Now you replace these units. Instead of having deterministic weights, you consider them as a random variable. So they have each unit has a distribution of weight instead of deterministic weight. So basically, what you have uncertainty that are hard-coded in each unit of the network. And when you train the network, you don't train it to get better weight, but better distribution of weight within each unit. So if you, for a single sample, you don't have one answer, but a distribution of answer, okay? So you have the uncertainty that is hard-coded, and you have directly an uncertainty answer to your network. The advantage, it is well-grounded theoretically. The most important limitation is that is much more expensive to train and to use, because you have to train for distribution within each unit, and each inference is not an inference. You have to run it multiple times to estimate the distribution of the output. So in practice, it's not very used because of this problem of computational load. There is some approximation to this, which is, for example, the Monte Carlo dropout. So I'm sure during the week somebody talked about the dropout layer. No, so dropout is just when you train your network, you set some of the unit to 0. Okay. During each iteration, you set some of the unit to 0, and then for the next iteration, you set all the units to 0, and you choose randomly which unit to set to 0. You iterate, and then you choose another set of units that you set to 0, and you iterate, and you backpropagate, and you train your network like that. So your networks become robust to the activation or not activation to any of the units of the networks. So it was a process that were dedicated for at the beginning for the training, making the network more robust. So it can be seen as a kind of regularization of your training. And this does work to have more generalizable networks, but it can be used also at inference. At inference, you can choose to use only some of the unit, have an output, then choose another set of unit, have a second output, and then you can have a set of output, which will the different output that you have is are the output that is the distribution of output that you have when you are uncertain of which unit you use. Okay, so you have a kind of approximation of the Bayesian neural networks that is much more efficient. The training is basically exactly the same as usually. You have few run that you need to do at inference, but then you get the uncertainty measure. Okay. Another way to do about the same thing is to do the ensemble learning. Instead of having one network, well, you train a set of network to solve exactly the same task. And for example, you initialize them. At the beginning of the training, the weights are initialized randomly. Then you just use different networks that are initialized differently, and you train them all. So the different output at inference that you have from each of the network can be seen as a distribution of possible answer, and then from this you can measure uncertainty. You can compute just the standard deviation of the map or the probability or the entropy, and it gives you an uncertainty measure. In practice, it works well. It's better than Monte Carlo dropout because it gives more accurate uncertainty measure, and you don't need to have a lot of model. Basically, with 5 networks, you have a very good result, and it doesn't really improve beyond these 5 networks. Limitation is that, well, you have more computation to do because you have a set of model to train instead of only one. Yes, but it's much less computationally demanding than, for example, Bayesian neural networks. Another way that you can use to do uncertainty estimation is test time augmentation. So now we are in the setting where the network is trained, and then so it's trained usually, and at inference you still want to have an uncertainty measure. So for example, here you want to do segmentation, and you will use data augmentation. So you all know now what is data augmentation. It's a way to improve your training, to add artificial data in your training. Now we will use it at inference during test time. So what we do is, for example, we have this brain that you want to segment. What you do is you give this brain to the network, and give the same brain with a transformation. So for example, an upside down flip can be any other transformation, can be rotation, can be left, right, can be any transformation that you can think of. And if you just do the upside down flip, obviously, normally, the segmentation should be upside down, also upside down. Then you can measure the difference between this, what you expect and what you get in reality. So you have the segmentation of the original brain, and you flip it upside down, you get the segmentation of the upside down image, and you flip it again. So you should get exactly the same. And then if you measure the difference, you get a location of where the two images, the two segmentation does not agree, and this is probably where you are uncertain. So you get uncertainty that way. So it's very easy to set up also, and it actually does improve robustness and accuracy, and it's mainly dedicated to estimate aleatoric uncertainties. And I have time to present you the conformal prediction. So this is another way to think about uncertainty. Here I will present you on the task of the classification. So now you don't want to, in the other method I presented you, you had the answer and you want to have a sigma, for example, to say what is the error here on the prediction. Now what we have with this conformal prediction, we replace the one sample, the one sample prediction by a set of potential candidates. Okay, so instead of having, oh, this is a squirrel, we have, well, it can be a squirrel or a rat or something, but we are not sure about that. So it gives you the set of potential labels that you can have as output of the network. So so formally, you want to find the set of label that, so the set C of I would be the image, such that the probability, you want to find all the label in this set, such as the probability to belong to this set is higher than 1 minus alpha, and where alpha is a value that you set yourself. So basically 0.1, for example. And so I will show you how to get all these this set. So what you need to do that, it's usually you have the training set, the validation set, and the test set. Now we had the fourth set, which will be the calibration set, which will be a data set with annotation that will be dedicated only to this task. So first, what you do is you have a calibration score. For example, it's 1 minus the output of the network, okay? You want this calibration score to be the lower for the better samples, okay? So this 1 minus the output, for example, will be very low for the predicted class. So when this predicted class is the good one, you're happy with that, you will have a very low S score. And the probability for this score, for a sample to have a score lower than a given threshold is exactly the same, if you look at the math, as the probability to a sample to belong to this set, confidence set, okay? And now what you just need to do is to compute this score for all the calibration data set, find the threshold that is associated to this alpha. So for 1 alpha, you get 1 threshold, Q, which is given by this formula. The math to get to this formula is not very complicated, but today I will not go into the details. And then you get this threshold. So when you want to use this calibration set is dedicated to find this threshold. Now, when you want to to have this set for a real sample, okay, so you compute the output, compute the score for these classes, and you just look, is it below or higher than this score, and it gives you all the label that should be returned in this confidence set. Okay. Okay. I don't know if I was clear about this part, but we can come back to that in the question, maybe. So the advantage of this conformal prediction is that, well, this is really mathematically grounded. You have the guarantee to have all the label that satisfy this condition, even if your softmax is not, if your network is not well calibrated. Okay, so it's a different way to have something that is calibrated, but it's not calibrated as I presented you in the beginning. It can be applied to any model. You can combine the score. You can combine the score with any other uncertainty measure. Here, I use the network output, but you can use any other measure to use with this method. The limitation is if your network is not good. Well, it's maybe not a limitation, but if your network is not good, you will end up with a very large output set, but it's because your network is very uncertain. So it's a limitation, but it's so actually can be seen as a good feature that it tells you that you cannot have the answer. It requires a calibration dataset, so you have to dedicate some data, especially for this task. And it's also very sensitive to the domain shift of the calibration set. And now I will let the floor to Valentine.
Okay. Can you hear me? Yeah, okay, perfect. So I will be following about explainability. Okay, so what is the explainability of a deep network? So if we take again a network, we can have different output depending of the task. For a segmentation task, we will have, for example, a lesion mask. For classification, we will ask whether if the subject is healthy or pathological. For regression, we will have a score, etc. And explaining a neural network decision means understanding why the network makes the decisions. So there are many methods for explaining the decision made by a deep network, which can be divided in different categories. So the first distinction is between model agnostic and model specific methods. So in other words, whether the method can be applied to any model or whether it can only work for certain models. Next, we can distinguish between global and local interpretability. So for global interpretability, we want to explain the model in general. So for example, it used this feature, wasn't this one. And for local model, we seek to explain the decision for a given input. So the feature which is used by the network, but for this image, for example. We can also distinguish post hoc method and which explain pre-trained models, and intrinsic methods which incorporate the explanation into the model using specific architecture, for examples. And finally, we can explain the decision in various ways by indicating the most important feature of the network, by generating some text to explain the decision, by providing example. For example, for an image, we have this decision because it looks like these other images, or we can use semantic concepts. So we will look at a few methods, and we will focus on the classification task in the following. So one category of method which can be used to explain a deep network decision is attribution maps. So these are post hoc methods, meaning they are applying to a trained network. And for a given image, we will have an output. For example, we can take the example of a healthy versus a pathological classification, and the output could be pathological. And we will look for which part of the image are the most important for the network decisions. So for the pathological classifications, which part of the image leads it to conclude that the image is pathological. So we will obtain an attribution map. So for example, here we have in red the area which are the most important to classify the image as pathological, and in blue as an healthy subject. And to construct this map, we can use different methods based either on gradients, activations, or perturbations. So if we look at first to gradient-based methods, so here we will examine the gradient of the network's output f of x with respect to each pixel in the input. So intuitively, the gradient indicates how each pixel influences the output. If we make an infinitesimal change to the value of that pixels, how does the output of the network change? So you have the formula here. So this method is referred as local, not the same global local as defined previously. And we can, if we multiply the gradient here by the input, in this case, we will have a global interpretability. And in this case, we will describe the marginal effects of the pixel on the decisions. Still based on gradients, there are methods that calculate the gradient along a path, such as integrated gradients. So here we need to define a baseline, often a null image. And then we will compute the gradient for each image, which is a linear interpolation between the image for which we wish to have the attribution map and the defined baseline. And we will take the average of this, all these gradients. This method satisfies a lot of properties. So sensitivity, implementation invariance, completeness, linearity, symmetry preservations. And if, for example, if we define sensitivity implies that if the image and the baseline differ in 1 pixel, and the network output is different for these 2 images, then the attribution for that pixel must be must not be 0. So the choice of the baseline will significantly influence the resulting attribution map and can be difficult to choose. Indeed, by definitions, the attribution map for the baseline will be 0. But which image should we choose as an image with 0 relevance for our task? It's quite difficult to determine. Various approaches have been tested, and no single solution appeared to be superior to all the other in all situations. And for that, expected gradient proposed using several baselines from the database to compute the attribution. So here you have an integral with of the integrated gradient attribution map with images in the database. So we can see the illustration of the different methods here, and we can see, for example, that for integrated gradient, by choosing a zero baseline, it is the case here, that is to say a black image, there is no attributions in the case. And it could be an issue if, for example, if your object of interest is black. So choosing for the classical null baseline could be a problem depending on the task. So gradient-based methods are very useful for explaining neural networks because of the differentiation modules already used for training. It's quite simple to compute a gradient with a classical deep learning library. However, this type of math can be noisy. So another approach to generate attribution map involve activation. So one method is SCAM for class activation maps. This method requires a specific layer at the end of the network. After the last convolution, we will add a global average pooling. This layer computes the average of the value for each channel of the last convolution layer. And then you will have a fully connected layer to perform the classifications. So with this fully connected layer, we will have a weight for each channel to compute the final decisions. And to construct the attribution map, we will simply multiply this weight given by the fully connected layer by the activation, the channel of the last convolution layers. And have the final maps. The disadvantage of this method is the use of a fixed classification head. You have to add this global average pooling layer. And so for that, to address this issue, GradCam proposed to determine the importance of each channel without the global average pooling. So we have just seen that the gradient can be used to obtain the importance of each pixel in the decisions. So we can use it also to obtain the importance of each channel of the last convolution layer. Another advantage of GradCam, in addition to not requiring a specific layer, is that it can be used on any convolutional layer of the network. In practice, it is often computed on the final layer, which contains more semantic content that is closer to the decisions. But it can be used on any convolutional layer of the networks. With these two methods, the resolution will be quite poor because if you take a deep layer, the size of the channel will be very small due to the pooling layer across all the network. And to restore the image dimensions, you need to apply interpolation. So the resolution will be poor. Finally, on activation-based attribution, in recent years, there has been a surge of the use of transformers. And in these architectures, there is attention mechanisms which learn an importance map. So as it learns an importance map, it had been proposed to use this map as an attribution maps. The most commonly used method is rollout, which allows to trace the flow of attention from a deep layer to the image. However, these attention maps are not class specific. It's the same for all the class of the networks. And to address this, we can weight the attentions by the gradient for a specific class. However, papers have shown that changing the weights in this map does not necessarily change the output, and high attention value do not necessarily mean that the associated area in the image is important for the decisions. This property are quite necessary for attribution maps. So these attention maps should be used with cautions, because they do not satisfy common property of attribution maps. Finally, another way to generate attribution maps is through perturbations. So it consists in perturbing the input image, for example, by setting a port to 0 and observing the impact of this perturbation on the network decisions. So this is the principle behind occlusions. And for example, here we have an image of a hummingbird, which is predicted, it's quite small, no, quite okay, with a probability of 93%. And if we set its head to 0, then it is predicted as a hummingbird with a probability around 0.5. So removing its head, therefore, have a significant influence on the budget prediction, which means the area is important, and so the attribution value should be high. Conversely, if we remove a part of its wing, the probability is around 0.9, and therefore is not greatly affected. So the corresponding value of the attribution map should be lower. So we will repeat this process for all the areas in the image, and the value of the attribution map for a given area will be the difference of the network output for the original image and the perturbed image in this area. So there are several techniques for perturbing the image: blurring, setting a custom value, for example 0, adding nodes, etc. And the choice of the techniques will produce different maps. The main problem with this method is that perturbation can firstly create an image outside of the distribution of the input level data, domain shift, meaning that the network will not be longer able to correctly classify the image. And another issue is that the modified area are often large to have a significant impact on the network and to reduce the computational cost. And in the result, the maps have often poor resolutions. Okay, so in the previous case, we modify the input with a given perturbation and observe the impact on the output. We can also search for the perturbations that cause a desired change in the output. So typically, we will want to change the class. This is not as counterfactual example generations. So starting with a trained network and a given image, we will look at to the minimal modifications to the image to change the output by switching from pathological class, for example, to LC class. And to do so, we will solve the following optimization problems. So we will seek for the alpha map of the same size of the input, such as if we input x minus alpha into the neural network, we will obtain the desired output. And we will want to minimize alpha also. This optimization will identify the most critical area for switching from one input to another. The problem with this type of method is that the generated counterfactual examples are often very difficult for humans to interpret. And if we take this example, so we have an image of a panda, which is predicted as a panda by a network with 58% confidence. And by adding the following nodes, the prediction of the image becomes a gibbon with almost perfect confidence. So now it's time to test who in the room is human, who see anything else than the panda on this image. Nobody. Okay, all humans. So this is what is used in adversarial attacks, and the modification made to the image are not visible by a human eye, but change the predictions. So in our work, we have proposed an architecture to improve the interpretability of counterfactual examples. So to achieve this, we use a monotonic network. So what is a monotonic network? So everybody should know what is a monotonic function. It's the same for a network. So here, for example, we will have a network with a gradient which is positive. So if we increase the value of the one pixel in the input, the output must remain the same or increase. Since there is not necessary a monotonic relationships between the input and the output in most of the problems, if you take, I don't know, MRI scan and it is LC or pathological classification, it's not because you increase the pixel in the image that you will be more pathological. So to solve this problem, we add an encoder which allow to go from the image space to a domain where there is a monotonic relationship between this domain F and the output of the network. So we use this network for LC versus pathological classifications. We also add some calibrations so that if so the feature here after the encoder are negative, the output is negative, and if it's positive, the output is positive. And again, we search for a counterfactual example. So we will search for alpha, such as if you take F minus alpha as the input of the monotonic network, the prediction become LC instead of pathological. And we will search the minimum alpha. And in the case of the monotonic network, because it's monotonic, we know that a positive alpha solution exists. And by seeking a positive alpha, we make the counterfactual examples much readable. We only modify the image in one direction, not both negative and positive modifications. And we also keep F with the same spatial dimension as the input. So the modified area in F are the most important for the decision in the image, in the input image. And if we look at to the results, so we can indeed see that the counterfactual difference alpha is more readable and interpretable with our method. If we look at to the baseline, so computed the counterfactual example with a basic method, we see that it's very difficult to understand what needs to be modified in the image. So in red, you have the positive alpha and in blue, the negative alpha. Whereas with our method, the region which should be modified to go from a pathological to an HC classifications is the area of the tumor. And this is consistent with what a human will do to go from an image with a tumor to an LC image. We want to remove, modify the area of the tumor. Counterfactual example can also be generated using a generative model. So for the example, in this paper, they use a diffusion network. So diffusion networks are generative models that generate image from noise, so Gaussian noise typically. And here again, they want to transform the image from with a tumor to an LC image. So to do that, they add noise following the diffusion principle to the image with tumors, and they only perform L steps, that is to say, they stop before having a perfect Gaussian nose, and then to keep some information from the input data, of course, and then they use the diffusion model to denoise the image, but by guiding the diffusion network using a pre-trained LC versus pathological classifier. So the result image is LC. So at each step, each denoising step, they proceed to the classical dezoning step with the diffusion model and pull it toward the LC class following the gradient of the pre-trained classifiers. Okay, so with the attribution map, we have seen that we can locate the area of the image that are the most important for the networks. We therefore answer the question, where is the important data, but not the question why. There is another type of explanation that allow to answer to this question. This is semantic explanations. So unlike attribution methods, these methods are often intrinsic, meaning they use specific architecture designed for the explainability. And generally, there is a semantic concept layer at the end of the network, and the decision is made with a fully connected layer that assigns a weight to each concept to take the decision. And during the inference, we can look at which concepts are the most important to take the decisions. So the main methods are concept bottlenecks models and prototype networks. So if we look at to concept bottleneck models, so traditional bottleneck approaches use predefined concepts specified by the user. So for example, if we take the example of the prediction of the severity of osteoarthritis, the expert can define a list of relevant concepts, for example, sclerosis, bone spurs, now joint spoils, etc. And then he will define the link between the presence of this concept and the severity. So for example, if there is a sclerosis and a wide joint space, then the severity is 3. The network consists of 2 parts. So an initial network that using the image produce a vector of concept activations, and the fully connected layers that assign a weight to each concept to make the decisions. And the network is trained using classical classification loss and a loss function to assign the correct concept to the image. So the main limitation with this method is the need for annotation. Ideally, you need to have a list of concepts for each image, and you must at least have the list of concepts for each class. So it's quite demanding. Several papers have proposed alternatives to reduce the need of supervision. So this is a case of self-explainable neural network. So here, which will learn concept without requiring a user-defined list. To achieve this, the architecture is composed of 2 parts. So you have the upper part, which extracts the concepts, that is to say, latent representations, and the lower part, which extracts the relevance, that is to say, the weight to be assigned to each concept. And then the concept and their weights, their relevance, are aggregated to produce the final classifications. To train the network, several losses are used. So you have first the classification loss. With the aggregated concept and relevance, you must have the correct labels. You have a reconstruction loss with the concept. You should be able to reconstruct the input image from the concept. It ensures that the information is contained in the image is preserved in the concept. And you have some regularization loss. So a first one about sparsity. to avoid some redundancy in the concepts. And a second one, which enforce local linearity between the concept and the relevance. That means if you modified a little bit a concept, you don't want to that the associated relevance to change significantly. So it allows to learn concept without supervisions, but by removing these supervisions, we end up with concepts that are very difficult to understand and lack semantic meaning. To interpret the concept with this type of method, it is necessary to first identify the images in the database that activate one concept, and then identify what they have in common to relate the latent representation of the concept to human readable meaning. Some methods also combine the post methods with some predefined concept and learned concepts. So in concept, in the previous approach, concepts are features presented in the image, but visual concept can also be used. This is a prototype. So in this case, the concept will be image patches from the database, and the explanation will be based on the example. This decision is made because the input image looks like this image from the database. So to do this, first, a number of prototype, so image patches, latent representations is set per class. And the aim is to learn the most representative patches for each class. So prototype network follows this architecture. So you have a first network which encodes the image. So you have compress the information. You have a latent representations. And then for each part of the image, we determine the similarity with each of the prototypes. So the latent representation of our reference images. We then have a fully connected layer that provides the final classification based on the similarity score computed previously. And the prototype are learned with clustering techniques. So you want that the image latent representation to be close to the prototype if the prototype and the image belong to the same class, and far if they belong to a different class. You have also, again, a classification loss. And so here the prototype are latent representations. To retrieve an image which is readable by human, we will use a decoder that maps from the compressed space to the image space. And finally, to ensure that the compressed representations correspond to images in the database, during the training, we regularly project the representation, the latent representation, on the real data. So we just replace the learned representations by the closest image in the database. So there are some methods that combine concept and prototype. So this is a case of this method. And here you don't you have not only a prototype per class, but also per concepts. So to explain the decision, we can say that the decision was made because the image looked like this prototype in terms of margin, this prototype in terms of duration, etc., etc. So you have prototype per class, but also per concept defined by the user. So here's the margin, the duration, speculation for tumor, long tumor classifications. So we have seen methods that answer the where question. These are attribution maps. We have seen methods that answer the why questions. This is a semantic explanation method. But there are methods that do both. And this is a case of with craft. So unlike the other semantic explanation method, here it's a post hoc method. So it's applied on a trained network. The only requirement is that the network has been trained using data augmentation that include crop patches, because it will use crop patches. So to explain the network decisions, we take a set of images for which we want to explain the decision, and we will feed the network with patches of this image. And we will retrieve the activation map just before the final layer in the network. So the classification, just before the classification layer. And then by concatenating the latent representation for all these patches, we'll obtain this matrix, so G of X. And the next step is to perform a non-negative matrix factorizations on this matrix G, where W will represent the concepts. This step is applied recursively. So we take, at the second step, we'll take the image that activates the same concept and perform this factorization again, but not using the final layer, but the previous layer in the neural network. And we will repeat this step several times to obtain sub-concepts. So here you have a database of concepts, and the importance of each concept is then determined using the Sobol index, which measures the sensitivity of the output to a small perturbations of the concepts. So if you perturb a little bit the concept, all the output change. So here you have a set of visual concepts. You have the importance of the concept, and to answer the where questions, the author use an implicit differentiation, so some gradient between the concept and the input to find where the concept is the most activated in the image, as we see, as we saw with the gradient methods. Okay, so to summarize, we have seen several methods for explaining neural networks, whether to locate the most important area with the attribution map, or to determine semantic concepts which are used by the network, or methods that combine both approaches. We can think that this is sufficient. For example, if we consider a healthy versus tumor classification task, and we would want the network to predict the pathological class for an image containing the tumors. And for the explanation, for example, if we use an attribution map to investigate the most important area for predicting the class tumor, and we want that the tumor itself to be highlighted. If I have an image with a tumor and the prediction is tumor, I want that the network use the tumor area. In practice, if we train a classifier on this task and analyze the attribution maps, they will not necessarily be focused on the area of interest. So you, for example, here, the attributions are located in some other regions than the pathological region. So here for multiple sclerosis, and here for brain tumors. For example, here is in the sulcus instead of the multiple sclerosis lesions. So why we have this type of map? Because the network may use some shortcuts to make its decision instead of clinically relevant information. You only give some data. During the training, no indication is given to the network which area should be used for the decisions. So it is therefore necessary sometime to force the network to use these clinically relevant regions to make these decisions. So in our work, we propose an unsupervised constraint for the healthy versus pathological classification task. So during the training, in addition to the classical classification loss, we force the attributions maps to be negative for LC images, meaning that all the pixels for an LC image to contribute for classifying the image as LC. Indeed, we know that for LC image, all the pixels are LC. So there is no need for additional supervision in addition to the label. It is LC or pathological images. And with this constraint, we obtain attribution maps that are much more focused on the pathology. So here for multiple sclerosis and for tumor images, the network use more clinically relevant features, that is to say the tumor itself or the multiple sclerosis lesions, compared to a classifier trained only with a classification and without need of supervisions, for example, manual segmentation. It's only an unsupervised constraint during the trainings. So it's very important to be mindful of confounder of short curves bases present in the training set that the deep network use to make their decision. Even we would prefer it to use relevant features. So for example, in this case, there is some annotation in the training images of the horse classes. So you have here some text. And if we remove these annotations, the image is no longer classified as a horse. Conversely, if we add annotations, this text on an image from another class, for example, here a car, the image is now classified as a horse. This clearly shows that the network uses this annotation to make its decision rather than a relevant feature. And we can see it on the attribution maps. It's the text region which is activated. So in medical imaging, there is many non-confounding factors, such as the presence of a pacemaker in a chest X-ray. There are some rules in skin lesion to measure the lesion size, etc. But there are also lesser known confounder that we need to be mindful. So in our work, we identify, for example, the brain shape as a confounder in brain MRI classifications. So we demonstrated it in 2 steps. So the first step was to answer the question, is it possible to distinguish the 2 databases using only the brain shape? So we take a lot of brain MRI dataset, and we see if using only the brain shape, we can distinguish various databases. And to represent only the brain shape information, we use brain mass, that is to say, binary images, 1 if the pixel is inside the brain, and 0 if it's outside. And we examine if we could distinguish between these different brain MRI datasets using only this mask. And the answer is yes. We achieve a very high accuracy across multiple datasets, whether classifying LC versus pathological subjects, so here tumor or multiple sclerosis subjects, but also when for LC versus LC classifications, and even when the age of the population was the same between the 2 databases we classify with. The only case where is it impossible to distinguish the data sets, it was the case of the intra-dataset classification. This means that the bias stem more from how the data sets are constructed rather than from clinical criteria such as the disease or some age-related brain atrophy, etc. And so with this experiment shows that it is possible to use the brain shape to distinguish between datasets, but note that it's used when the MRIs are provided as input. So we therefore propose a second experiment to answer this question. So during inference, if the image is modified so that the brain shape falls within the distribution of the opposite class, the opposite database, can we still distinguish between the two databases just as before? So to modify the brain shape according to the distribution of the other class, we randomly select a brain mass from the other database, and we apply two transformations, either a crop, we just remove set to 0 the pixel outside the selected mask, or a registration of the border of the brain. And so with this transformation, we produce an image with the same content, but with a brain chain from the other class. And so if with here you have the results, so if you just classify on the original images, you have a perfect classification, one for the positive class, negative class. And if you modify the brain shape either with a crop or the registrations, you can see that the performances are slightly are very impact. Here you have the accuracy, which is very low. This means that the network indeed use the brain shape to make its decision. If you modify the brain shapes at inference, it is not able to correctly classify the image. So the brain shape is a confounder. So to eliminate this confounding factor, we propose an additional processing step to normalize the brain shape using deformal registration. So we just perform a deformal registration on the border of the brain with an atlas. And with this normalization, we can see that modifying the brain shape during inference no longer impact the classifications. So here, for example, you have the performances here. And the brain shape is therefore no longer a confounding factor with our proposed shape normalizations. So in the previous approach, we have proposed a solution to remove the confounding factor from the images before using them for the training and of the neural network. It is also possible to train a neural network to not use a confounder. So for example, in this paper, the author used 3 neural networks, a feature extractor, so here in orange, LC versus a pathological classifier in blue, and a confounder factor predictor in red. And to train the network at each epoch, the weight of the feature extractor and the classifier are optimized to correctly predict the label to perform the classifications. The confounder predictor is optimized to predict the presence of the confounder, but only using the LC subjects. This prevents the pathology to be a confounder for this confounder predictor. And finally, the feature extractor is trained using adversarial training. So it's trained to produce an output to fool the confounder predictors or the red network, making harder to correctly predicting the confounder. In this way, the feature extractor will learn representations that does not include the confounder. And the author evaluates their method on LC versus HIV classification tasks with the age as a confounding factor. So they train on dataset containing the age as a confounder and evaluate on a dataset without the confounder. So we can see that without their method, the young people are misclassified, whereas with their method, they are correctly classified. So it means that the network learn the confounding factor rather than the relevant feature without the proposed method, and with the proposed method, it learns the real HEV features for the classification. We can also see that the confounder have an impact on the latent space. Without the confounder free training, in the latent space is structured according to the age. Here you have the age in yellow, older people. And in the case of the confounder free training, there is no more structure according to the age in the latent space. And that is for explainability and for the presentation of the school. Thank you. If you have a question, we have some time. So.
Thank you, Micheal and Valentine. Questions? We start by Isidore.
Thank you for the presentation. I really appreciated both. About the last slide and the confounder, is it so different from domain shift? Because it really lacks domain adaptation method.
It's not exactly the same thing because domain shift here for the confounder, you think you train if you take the introduction slide up, you think you train on something. For example, here you think that you are training on the shape, and instead of training to distinguish the shape between the two databases, you learn the color. It's not the same because here, if you take this database, you have good performance. You will have good performances, but not based on the good feature.
So you have identified the different confounder before the training?
Yeah. Most of it's very difficult to learn a confounder-free network without identifying the confounder.
But after you define the different confounder, like a brain shape,
yeah,
and it's relative to the different data set. So it is
in both domain shift and confounder problem, you will have a lack of generalizations to other data set. But it's not the domain shifts. You change some parameters. Here, it's just you think you train on something and you learn something else.
Okay.
But the consequences are the same. You are not generalizable to new data sets.
Okay, thank you for the presentation. I appreciate it a lot also. I have a few questions, but I have to limit myself about the questions. About the co-founder again, here in your experiments, the problem because the classes are not distributed the same way depending on the type of class, for example, for young or old people. Is it that the problem, or even for the brain shape? If the distribution is the same, the decision of the network will not be affected. If the distribution is the same, yes, it will not be affected by the confounder.
Yeah, but here what we notice is that the distribution of the brain shape is different across different brain MRI datasets. So here is almost all public datasets.
And also across classes, I mean LC, non-LC, or something like that. They are different. The distribution of classes across
because
datasets are different.
Yeah, you can distinguish from the brain shape from LC dataset from, for example, a tumor dataset. So we can think, okay, it's normal that there is a difference between healthy and a pathological subject because the tumor can deform the shape. For data set without the same age, maybe there is brain atrophy. But we see that even if both data sets are healthy, even if the age matching, we can distinguish between the two distribution of brain shapes. So with the hypothesis behind that is the bias stem more from how the data sets are constructed, because we cannot distinguish is here a pathological, so it's for Alzheimer's disease, and a healthy data set if they are constructed in the same way from the same data sets.
Okay, so it doesn't come from the data itself, but the way that the data is presented post-processing, post-process on
because when you
okay, I understand.
Data,
but there, I have another more fundamental question, which is some confounder could be part of the knowledge that you could use to decide the class. For example, if you have young people, you may look not the same part of the brain if you look at old ones. So if you remove this age in the features, you will be you will remove some useful information. So what?
It's depending of the task, you have to decide if this feature is relevant or not for the task. So you are not obliged to apply our proposing step if you think that the brain shape could have.
But maybe you don't know.
Yeah, maybe you don't know.
Okay. For example, you have lower results when you know like that, or but if you remove some features, it's normal to have less. Okay. Okay. Thank you.
Hi, thank you. So I had a question on calibrating models. So these days, mostly the status quo is, especially in medical or other domains where we don't have lots of data, you use a pre-trained, like a big foundational model, and you mostly freeze it, or you just have a few layers or adapter layers, and you train it not too much, and you train it on few data. So do the techniques like label smoothing and the temperature scaling still hold? Because I would assume that well, I don't know, but if the models are overconfident, probably this overconfidence comes from the pre-trained backbone and not necessarily the few layers we fine-tune.
Yeah. Regarding this calibration method, specifically for foundation model, I didn't check the literatures.
Okay.
Everything can be done exactly the same way, but obviously, if you have a very constrained settings where you have very few data, well, in this case, well, these are not perfect and exact methods.
Okay.
So they will improve the calibration. There is no guarantee that your model may be foundation model or any model. There is no guarantee that the model after that will be well calibrated, but they can improve. And I don't see why you wouldn't improve on foundation model and on only fine-tuning the lower, for example, layers or stuff like that. So,
okay, no, it's interesting, something to try maybe.
Yes. I guess, well, there is nothing that are specific to any architectures or stuff like that. So I think this should improve, but I didn't look in the literature if there is some specific works on that.
And just a quick question on a similar topic, but to Valentine, was regarding all the attribution map techniques. This was for classification tasks. And if we talk about segmentation task, so we're predicting a mask, but the mask is, the classification of the masked area region is wrong. And and if we plot out the attention or whatever, likely the mask region is correct, but the classification is wrong. So what can we do to gauge like the explainability, or why was this mislabeled, this class versus the other class?
Yeah, indeed, for a segmentation method, you have the field of view to predict this pixel is I don't know, from the tumor versus from the background. You know that the decision is made by the pixel in the field of view. So attribution maps are less useful in this case. But some paper use attribution maps also for segmentation to see in detail in the field of view which are the most activated. If you have a big field of view, you can reduce your area of interest using attribution map, for example.
Okay, makes sense. Thank you.
More questions? No? Okay, perfect. We can thanks again Valentine and Micheal.